So, hi everyone, my name is Tomer. I'm an engineer at Yelp. I've been at Yelp for about 4 years now, and for the past 2 years I've been working on our public API and our internal APIs. More recently, I built GraphQL as part of our public API that we launched this past May. So, if you're not familiar with Yelp, Yelp's mission is to connect people to great local businesses. So we want to be able to help you find your next favorite bar, next favorite restaurant. And my goal as part of building the public API is wanting to help third-party developers integrate that functionality into their applications. So in the beginning, we had this API that we called API v2. API v2 was pretty massive. It was actually only 3 endpoints, but there was hundreds of fields in each endpoint. This is me kind of just scrolling through it. So last September, we rebuilt the API. We launched a new API called Yelp Fusion. This was v3 of the API. And one of the first questions we got was, well, can you add this data back into the endpoint? Or can you add this other data back into this other endpoint? And if you're building an API, you know it's kind of a pain. You want to be very RESTful. You want to have a good API design. You put a lot of thought into what you build so that it's easy to use, it's easier to understand. And it was kind of a bummer to see people wanting all the data all in the same endpoint again. So this is where GraphQL came in. If you're not super familiar with GraphQL, GraphQL is a query language for your API. So that means it gives you the flexibility to request any data you want, structure the response however you want, so on and so forth. So what does this look like? On the left is a sample query, and on the right is the data that the API would return. So somebody could come in and get the name, alias, and rating for the business Yelp and do that no problem. Somebody else could come in and get the reviews data, no extra work on your backend. You don't need to spin up a new endpoint. Someone else could come in and say, well, I don't care about the alias, but I do want hours. Totally fine. Someone could come in and say, well, I actually want to get multiple businesses in one request. Normally, this would be 2 different REST calls, but with GraphQL, you have the ability to set up an alias and just make one request. Or you could come in and do something really crazy like this, where you get the categories of businesses of users who wrote reviews on the Yelp business. Why you would ever want to do this, I have no idea, but if there's one thing I've learned building APIs is that you're never going to be able to guess what functionality your users want. So let's just start with some basic vocab to make sure that we're all kind of on the same page. So query is the representation of the data you want. It's what I showed you a few slides back. This is what you send into the GraphQL API so they can process your request. The schema is the representation of your data structure. So this is what you store on the server so that the server knows how to respond to specific queries. Fields are the attributes available in your schema. All of your data and your requests are going to be tied to these specific fields. They're going to be corresponding to the data you get back from the API. So in this case, business name, alias, and rating are all different fields. A business might sometimes be called a root query or a root field because it's the top level most field. And lastly, you've got resolvers. Resolvers are the functions that retrieve data for a specific field in the schema. These are effectively the workhorse of a GraphQL API. This is where you're going to be doing all your data loading, all your data munging, any data manipulation you need to do. It's all going to happen inside of these resolvers. So how does this all kind of hook together? How does this all work? Our setup at Yelp is basically just this. So we have a dedicated service that runs only the public API. It runs Python 3.6, so the latest and greatest. It uses the Graphene library, which is the Python implementation of GraphQL. It's fully to GraphQL spec. We run on Pyramid and uWSGI. Pyramid, if you're not familiar, is Python's version of Sinatra or Express. uWSGI are the web workers that run all the code. We have a pretty complex microservices architecture. At the time as of right now, we've got a couple hundred services in production. I don't know what the actual number is. And the public API itself has no attached database, so it does not own any of its own data. It goes into other services to load everything. I'm going to focus on these first 4 points right now and show you how we actually built the GraphQL API itself. So let's start with this. This is just a simple post in the GraphQL endpoint. We're going to get the business name and reviews for the Yelp business. This is the view, a slightly simplified version of view. I took out some of the things like checking if you're in the beta or doing the request decoding, but it kind of still gets the point across. The first interesting part of this is this decorator, this verify API access. If you're not familiar with Python, a decorator is effectively a function that wraps the execution of another function. This specific decorator just checks that the request is authorized to use the API itself. The decorator looks like this. It's not doing anything crazy. This is not GraphQL specific, but this will come up again in a little bit. The gist of what's happening here is we're pulling the access token out of the authorization header. We're sending that access token downstream to our OAuth service to verify that you still have access to the API. And if you do, we inject your client into the request, and we continue on with the request itself. So the bolded wrap function is actually the GraphQL view I showed you before. You can see inside of that return statement that it's actually getting executed as a function inside the decorator. So back to the view. The first thing we do is we're going to instantiate the GraphQL schema. This is going to be all the root queries that you expose through the API. This looks like this. The query class defines all the top level fields, as I said. There's nothing too special going on here. The search query has another 10 query arguments that I had to cut out because they don't fit. And there's another couple other root fields that I had to remove too because they also don't fit. Things like reviews and phone search and events and all that stuff. These are all the root level queries that are going to be defined. So diving specifically into the first business one. So we're defining a business called, or we're defining a field called business. The first parameter inside of that field is the business class. That's actually going to be the business schema that the GraphQL returns. Every argument after that is going to be the arguments that the GraphQL API supports. So we have alias, and we define that as a string. You can already get the sense that GraphQL is going to be very strictly typed. This is the resolver for the business field. So as I mentioned, the resolvers are where you're going to be doing most of your work. The first thing we do here is we actually specify a decorator for this specific resolver. This is a little bit different than the one I showed you before, and the reason we're doing this is we have to rate limit GraphQL differently, so we have this additional decorator. Mostly doing the same thing. There's an extra check for GraphQL. Next up, we start loading data. So as I said, we've got a pretty heavy microservices architecture. We load everything through different services. And what we're doing right here is actually instantiating our internal API client to go into the internal API service. And then we're making a request into that internal API service to convert the public-facing business alias to our internal representation of business data. And next up, we have this data loader. So data loader is actually going to be loading the data from the service itself, but I'm not going to cover data loaders quite yet. I'll come back to that. So that's what the business resolver looks like. Back inside the view, we actually extract the locale from the header. We're using the accept language header to define that locale. If you've used accept language before, you might know that it uses actually a weighted list of headers, but we found it easier to just accept one header. With GraphQL, you're able to set some global state variables. These are generally going to be referred to as the context, and they're passed into each individual resolver. Resolvers don't have any information of the execution itself, of the overall query, so it's good to pass in some state sometimes. And then lastly, we execute the query. So with the original GraphQL query I had, this is going to go into the business resolver. It's going to start executing code, and then the business resolver, since it's going to return that business schema, is going to start executing this schema. So with the original name and reviews that we requested from the GraphQL query, it'll hit both of these resolvers, return the name and the list of reviews that are associated with it. So from top to bottom, this looks like this, basically. So the query comes into this view, it hits the query schema, which will match against specific resolvers inside that query. Those subsequent resolvers will match additional resolvers, which will eventually hit a data loader, which will eventually go into the service. So what's all this stuff about data loaders that I keep talking about? I've mentioned a few times and haven't really explained it at all. So GraphQL is just a spec. It doesn't really define any of the underlying technical implementation. Since resolvers don't have knowledge on the query itself or the subsequent execution, they get into this problem that sometimes people refer to as the N+1 problem. So the N+1 problem is the inefficient loading of data by making individual sequential queries. So if we have a bunch of cats and we want to get all their hats, then it's more efficient to do two SQL queries where you do select star from cat, where you get all the cats, and another query where you do select star from hats, where cat ID equals 1, 2, 3, so on. So you're saving yourself a lot of work by making two SQL queries instead of multiple ones, which is what's happening here. So in the GraphQL implementation, you have this problem naively. So in this specific case, we're requesting 6 different businesses. We want to get these all in one request from the GraphQL API. On the GraphQL's backend, it might end up making 6 different requests into the internal API backend. This is very, very bad, and at any volume is going to be a great way to DDoS yourself and take all of your applications offline. You really don't want to do this. So this is where data loaders come in. So data loaders are an abstraction layer to load data in your resolvers. They handle batching IDs and deferring query execution until all of your data has been aggregated. So it will not run an internal API request or any service request until it sees that the query has been fully parsed and has all the data it needs to. So going back to this query where we were trying to get 6 businesses in one go, instead of taking these 6 sequential requests, we can then turn them all into just one bulk request. This saves a lot of work in your backend. So inside the view, what we ended up doing was we defined a field on the context called Dataloaders. This Dataloaders class is very, very simple. It's actually pretty dumb. It doesn't do anything outside of just map a bunch of Dataloader names to the instantiated Dataloader model itself. This goes back to Resolver is not saving any state and not having any shared state, so we want to make sure that we instantiate all the Dataloaders up front. Dataloader looks like this. All in all, it's actually pretty simple. It's inheriting from the parent Dataloader class and then saving the locale if it accepts one. The key thing that's happening here is inside of this batch load function. So batch load function is going to get the list of all the IDs that the GraphQL API has been aggregating over the query of over the duration of the execution. The first thing that this one's specifically doing is it's doing the skip businesses info call, which is going into our internal API to get the business data in one request instead of many. It converts that response into a BizID to BizData map. And then the last thing it does is return a list of promises in the same order that the business IDs are initially passed into the batch load function. Returning the data in the same order is very important because the data loaders expect the data coming out to be the same order as the data going, the same order as the data that came in. If they're not, then you might hit sync issues on the data being returned to the user itself, which would cause a lot of problems downstream. So inside the business resolver, we can now see what this data loader is actually doing. It's calling that initial data loader class that we set up earlier, specifically the business one, and hitting that load function. That load function is what's actually aggregating all of the business IDs that you're making or that you're sending into the API itself. So that covers a lot of our actual API view code. Next thing I'll discuss is the service infrastructure. The service infrastructure is actually one of my favorite things about GraphQL. I think it fits really nicely with most service infrastructure, but you do have to build towards it. So there was a lot of considerations when we started building the GraphQL API. One of the first things is caching. Caching is always a problem on APIs. Requests are going to be pretty different, pretty unique. Performance becomes a bit of an issue. People can send in pretty large queries. They can slow down your backend. It can get a little messy. Complexity, always an issue. There's a lot more to explain, a lot more to understand. Rate limiting doesn't work on GraphQL APIs like it does on most REST APIs. You have to kind of think towards how GraphQL returns data and how it executes. Security is always a problem no matter what you're doing. You always have to be thinking about security. And the last thing is error handling. Error handling on GraphQL is a little bit different, and I'll explain why in a second. So let's start with caching. Caching APIs is pretty difficult. Caching GraphQL requests is going to be even harder. Requests coming into an endpoint are going to be very unique and have a large diversity. So you're not going to be able to set up a lot of cache entries per specific requests. A lot of caching strategies won't fit GraphQL APIs and will become very expensive very fast. So as an example, this is pretty easy to cache. You just want the name of a business. You can do that no problem, right? What if someone else comes in and says, well, I want the name and the rating? This would probably have to be a separate cache entry because you're storing more data for a separate request. But you're still storing the majority of the same content. It's a little bit wasteful. Features like search are particularly bad with caching. There's a lot of different variables that can come in, and you want to make sure that you can catch all of them. So this is a simple service request. Somebody just wants burritos for this latitude and longitude. Someone might come in, send a slightly different location. Maybe their device is older, has a worse GPS, so it's off by 0.001. Backend's probably going to be doing the same amount of work, but it's going to be a different cache entry. Or maybe someone's autocorrect kicked in. They're now returning a burrito with a capital B. This might look like a different request, but again, backend is still doing the same work. This is 3 separate cache entries inside of your cache for the same exact data. Data might be pretty large. It's not very efficient. Gets really expensive really fast. You don't want to be doing this. So at Yelp, what we ended up doing was set up this service called Spectre. So Spectre acts as a proxy in between services, and it's a caching proxy. So when it sees a request that it's seen before, it can serve you that cache. This can grab any service and applies globally to any request coming in. So caches are shared between services, which is pretty awesome. If somebody else has already warmed up the cache, I get to leverage that. Spectre caches are set up per endpoint, which means that you can pretty much set up a cache per data loader that you set up, since each data loader is likely going to be corresponding to one specific endpoint. This gives you a lot of control and a lot of flexibility on how you want to cache specific data. There might be a case where you want a data loader not to be using cache data because it needs to be very fresh, and the data loader can handle that no problem. So this looks like this. It basically just sits pretty invisibly from the data loaders to the service itself. As a service owner, we don't have to do any specific setup. We don't have to do any code modifications to actually handle this. Similarly with other services, on the left is the GraphQL API, and on the right are multiple services. All these services are still hitting the same Spectre caching service. So any cache that is already built up, we can still leverage. So at the top is a regular service call. The public API data loader is going to make a request into the service. It's going to get the response back. It's fairly straightforward. The middle is a cached service call. So the public API makes a request to the service. Spectre intercepts that request. It sees it has a cache for that request, and it returns the data. The service never sees that initial public API request at all. On the bottom is a cache miss. So the public API will send a request to a service. Spectre intercepts that request. It does not have a cache for that specific request, so the request continues on to the service. The service then returns the data back, and both the public API gets the data it needs, and Spectre gets an updated entry for its cache for future usage. So what about bulk data? One thing you probably noticed is data loaders are built to handle bulk data, so we need a way to work around this. This means all the requests going over the wire are going to be bulk data loads. If you've ever thought about caching bulk endpoints, you know it's pretty hard. The list of IDs coming in might be slightly different. They might be out of order. It's pretty frustrating to deal with. As we move towards bulk endpoint internally for a lot of use cases, we wanted to be able to handle this pretty well. So what we ended up doing was we built a configuration option for Spectre to handle bulk caching. This required a little bit of a change in how we think of caching. So what we ended up doing was we created this concept where for bulk endpoints, you don't cache the entire response, but what you're doing is you actually cache a key value mapping, where the key is the ID of the specific object you want, and the value is the data associated with that specific ID. So when you make a request into the bulk endpoint, cached by Spectre, Spectre can check and see what IDs it already has cached. Maybe it already has IDs cached for half of the request, but not the other half. In that case, what Spectre will do is it'll use the cache for the half of IDs that it does have cached, and for the other half, it'll pass them on to the downstream service. So you still get a performance boost by not having to load all the data up front. If Spectre does have the entire ID set cached, then it just returns the data to you immediately. Overall, it's still a pretty big win-win. So what's the configuration look like? It's just this. So you set up a TTL, you set up a pattern to match, you specify that you want bulk support, and you have this thing called the ID identifier. The two key things here are the pattern and the ID identifier. The pattern is doing some pretty gnarly regex, so I'm not going to dive into that. But what you're specifying for Spectre is the path you want to cache, and then you're specifying the grouping of IDs that you want to match on. Spectre will pull that group of IDs out, parse it, usually going to be a comma separator or something like that, and then it knows which specific IDs it needs to care about. The ID identifier, on the other hand, is the field that Spectre searches for inside of the response to know what objects it has to cache. So you're specifying what JSON key that it needs to look for to cache the data. With this setup, we've been able to set up a caching strategy that works pretty well for us, that doesn't involve a bunch of unique cache entries, that doesn't make caching super expensive. So what do you do when you have a bunch of cache misses or the query execution is still really slow? So we've started rolling out this idea internally called request budgets. What request budgets are a maximum execution time on a request, pretty similar to a timeout. The difference with a request budget and a timeout is that every downstream service still knows how much execution time is allowed to continue. So high level looks like this. It's pretty straightforward. You set an initial request budget of 1,000 milliseconds. Something in the middle takes up 470 milliseconds, so you still have a request budget of 530 milliseconds for every downstream service to execute. On the other hand, you might set a budget of 1,000 milliseconds. Something sleeps for 1,470 milliseconds, and you're out of budget. You're already 500 over. Every request downstream knows not to execute and should just fail up front and fail immediately. Request budgets give us the ability to kill arbitrarily complex queries that somebody might be sending into the API. Execution time can balloon immediately, especially on very deep queries, so you want to be able to limit how much damage somebody can do if they are actually trying to do that. So what causes these slow queries? Like I said, flexibility comes at a cost, and that cost is usually going to be complexity. When you have the ability to build any query you want, you have the ability to build any arbitrarily complex query. That might be a 10-deep graph, or it could be 4 circular references. This will very much cause your query to get very slow. So throwing back to the query I showed you all at the way beginning, this is an example of that I used to show flexibility, but is actually a very complex query to execute. It's also very expensive for us to do. Each layer of this query would likely introduce another network call and introduce another layer of fanouts, so that we're loading the reviews by users, by businesses, and by the time we're all the way down to categories, we're probably loading thousands to tens of thousands of different nodes. If you're trying to, think about how that would look on a database. If you do a select worth 10,000 different IDs, you're probably going to cause some slowdown. If you're doing this over like 1,000 QPS, it just cascades. So if we go back to this graph, there's a layer here that I didn't talk about at all. It's called the execution layer. The execution layer is what actually handles taking the query, running the resolvers, building the abstract syntax tree, getting the data loaders, and so on. The reason I didn't visualize this here is because it effectively wraps every single part of this, and it's hard to actually visualize inside of a graph. So the execution layer can have different execution strategies. Maybe we want to execute everything with blocking sequential calls. Maybe we want to make all the requests fully parallel. Maybe we want something in between. The GraphQL spec itself says the resolution of fields must always be side effect free and idempotent. The execution order must not affect the result, and hence the server has the freedom to execute the field entries in whatever order it deems optimal. What this means is that without building a custom execution strategy, you likely have no say at all in how the query gets executed. If for whatever reason the service decides to do something very unoptimal, you're kind of just stuck with that. For now, we've opted to leave all of our queries as blocking sequential calls. This is the safest on our system, and with the caching we've put in place, has worked out pretty well for us. So, rate limiting. One of the things you can do to help curb the amount of arbitrarily complex queries that people send is through rate limiting. Rate limiting is very important on public APIs, but is also still pretty relevant on internal APIs too. Rate limiting on GraphQL is going to be pretty different than how you do handle normal REST APIs, just because of how the execution handles the data it returns. I'll share some of what we've been thinking about and what we eventually settled on. So normally on a REST API, you have one request. One request is always going to be one request. It's very easy to measure. The work you do for that one request is always the same. The user making that request has little to nothing they can do to change it. If someone decides to send 10 requests, it's all still the same amount of work. Each search request here is still doing the same thing on the back end. This would end up counting in total for 10. So with GraphQL, you might start something like this. It's pretty simple. They just want the name on a business. That's still one request. I can count that. I know what I'm doing. But what if they come in with this? This is still one request. This is still a single post query to your API, but they're loading 3 different businesses. This is 3x more work than you might normally be doing. On a REST API, this would be 3 different calls. You'd have to go in and get each business individually. And what about this query? On the REST API, you can't pull reviews data inside a search. But here, they've opted to just pull all of that in one request. This one simple query is actually replacing something like 21 different REST API calls. It's great for the developer because they're able to do this in one query. That's awesome. But it's bad for us because we're doing a lot more work up front, or we're doing a lot more work on the back end and not counting it like we used to. So the first option we presented is node-based. So instead of counting the query itself, send as many queries as you want, but count the individual nodes returned by the API. So search counts as an individual node. Business would count as a group of nodes. The search query tends to return 20 businesses, so there would be 20 nodes returned by the search call. And reviews would be another group of nodes. We generally return 3 reviews per business, so this would be a group of 60 nodes. In total, this query would cost you 81 total nodes against your daily total. This matches pretty closely to the actual work we have to do on our backend for actual network requests we make to different services, but doesn't match perfectly one-to-one. Sometimes a resolver will have to go into its own service, and we can't count an individual resolver execution. The next option we looked at was field-based. So instead of counting the nodes, you count literally every individual field returned by the request sent to the API. So they requested the name and ID off of businesses on search. The response looks something like this. Don't worry, it's a little too small, I know. But the idea is that every single time the name and ID field appears, you would count that against their daily total. This maps very closely to the amount of work you do on the back end. You never do more work than what you charge for the user, but this becomes a little bit harder to measure. We did not go with this. We opted for the first method, for the node-based. It gave us a nice mix of relates pretty closely to the work that we have to do on our back end, while still being pretty simple for the user to estimate how much they're going to use. With field-based, there might be some situation where resolver only executes conditionally. Maybe sometimes there's less data, so resolver doesn't hit as often. It would get to a point where a user would just not know how to count the data coming back from the API. So GraphQL's flexibility is both a blessing and a curse. Securing the API is always going to be important, and I covered these first 3 points already. They're pretty important to actually making sure that you can sustain a GraphQL API. The next thing I'll cover is limiting the maximum query size. The bottom 2 I'm not going to cover. They're pretty big topics in the community. They're probably talks each and of themselves. You generally want to have per resolver level authentication, especially if you're exposing any kind of social app or anything that might involve different users having access to other users. You want to make sure that people don't just build graphs that execute arbitrarily and return all the data. With persistent queries, the idea behind persistent queries is that you might want to expose mobile APIs or front-end APIs, but you don't want people to be able to go in and crawl your private API effectively. So what people have started doing is they build predefined whitelisted queries that they save on their backend, and people hit those specific queries and execute that. So like I said, not going to dive into that anymore. But what I will talk about is maximum query size, or maximum query execution size. This is luckily pretty easy for us to do, and limiting your max query size is a fairly simple way to ensure that people don't send requests that would effectively do a select star on your database. Most valid use cases will have query size that are small to moderate in size. Maybe you do want a larger query, but with persistent queries you can work something around that. The small and medium queries are still small enough that they wouldn't have a large impact on you and still be effective enough for anyone downstream to use your API usefully. GraphQL lets you do this thing called middleware. So you can define middleware on the execution of your API, and it'll wrap the execution of resolvers with some code. So you can see specifically here, this return next call is actually executing each resolver that the GraphQL syntax tree is sent in. With this, we're able to say, cool, we want a max size of 2,000 resolvers executed. We can instantiate this middleware. Every time we execute a new resolver, we increment +1. If we see for the duration that we're less than a max size, we can continue executing, but as soon as we're greater than it, stop. Do not execute anymore. So what actually do you do when you start having errors? So the cool thing about GraphQL is that requests can partially succeed. If you're very used to building a REST API, you might be asking yourself, what am I talking about right now? Query execution is not all or nothing. The slide I showed you before shows that each resolver executes on its own. GraphQL takes this to an extreme. If a resolver fails, the resolver is the only thing that fails. The whole query can still execute. So normally, if you try to get hours on a business and the downstream service is serving 503s or 504s, you might just bubble up the 503s or 504 to the end user. But GraphQL will catch that failed resolver, just drop it, and insert an error statement inside the response. So this is still an HTTP 200. You have this new field called errors field, and it gives you this thing saying hours couldn't load, which is great. Maybe your upstream application can still work with partial data. We don't need to have a completely poor experience by degrading the whole application. But that does make some other failure cases a little trickier. So what if someone comes in and says, I want 123 Fake Street? This is obviously a fake business. This doesn't exist anywhere. Normally, you would be returning an HTTP 404, right? But GraphQL doesn't do that. GraphQL still returns an HTTP 200. Data is null in this case, but there's an error field that says business not found. So HTTP status codes on GraphQL are not necessarily used as much. It's now up to the upstream clients to parse the response to see if there is an errors field and to determine how to handle the error based on what the failure is. You can still use status codes for some failures. We still use them in a couple places. So we will still return an HTTP 429 if you hit your access limit. We'll return an HTTP 500 if we have an outage, or maybe a 503 or 504 if the service itself is unavailable or is timing out. And that's actually my whole talk. Hopefully that gives you all good starting points for conversations or questions to ask as you start to look into GraphQL internally. I wanted to give a quick mention. My colleague Nicola is giving a talk tomorrow at 11:30 in room 6. If you guys ever build Android apps, good way to see how we are able to build consistent UI consistent Android apps.